If your exam is coming up soon and all the aldol reactions are starting to blur together, breathe. This is the calm version. I'll walk you through the self-aldols of aldehydes step by step, explain why enolates really aren't that scary, show you where the stereochemistry comes from, and leave you with the one follow-up that keeps crossed aldols from becoming chaos. Hey there, ninjas. Today, we're going to work through the classic self-aldol of an aldehyde with sodium hydroxide. The product is a beta-hydroxyaldehyde. Our goal today is simple. Leave with a mechanism you can reproduce calmly on an exam. As the first step to a calm mechanism, we need to talk about enolates. I have an entire video that I'll link to down below that encourages you to take the enolate off of the pedestal. With that new perspective, the aldol addition is a reaction of an aldehyde or a ketone and a preparation of a beta-hydroxyaldehyde or ketone. One of the most common places in the mechanism that trips students up is right here in step 1. If you didn't know anything about enolates or about the aldol addition, and you saw a carbonyl with a strong nucleophile like OH-, you might be inclined to have OH- directly attack the carbonyl and kick electrons up onto oxygen. That's a very logical thing to do. Can that happen? Yes. Will it happen? Yes. A lot, actually. That's probably the most common thing that happens initially when you mix these two together. The OH- can definitely attack the carbonyl, kick electrons up onto oxygen. After a quick proton transfer, we form a hydrate. The problem is, hydrates are not thermodynamically stable. I tell my students, hydrates are things. They're things in biochemistry. We will see them again. They're just not things in organic chemistry. For a standard organic chemistry reaction, the formation of the hydrate is very much disfavored. The steps to form the hydrate are reversible, and this equilibrium strongly favors the carbonyl. But if that was your first thought, if that's one of the reasons this reaction is so confusing, I understand where you're coming from. The red flag we need to keep in mind is that hydrates are not stable and they'll go back to the carbonyl, so we have to do something else for our mechanism to move forward. And that something else is proton transfer, where we take the hydroxide and we deprotonate the alpha proton, break the carbon-hydrogen bond to form a carbon-carbon double bond, and push these electrons all the way up onto oxygen. And this is how we form our enolate, our key strong nucleophile for the aldol addition. There's two things to talk about with the enolate real quick. The first is that the enolate is resonance stabilized. And the second is that this is a proton transfer acid-base step, which means it's an equilibrium reaction. If we look at the acid on the reagent side of the arrow, that is the alpha proton, and alpha protons have a pKa of around 20 or so. If we follow the bouncing proton, the conjugate acid on the product side of the equilibrium is water, with a pKa of around 15 or so. In measuring acid-base equilibrium, the weaker acid always wins. If you need a refresher on pKa's and acid-base equilibrium, I have an entire acid-base playlist that I'll link to down below. But comparing these two pKa's, the initial alpha proton is the weaker acid. This equilibrium favors the reagent. That's really unusual. That's kind of weird. The whole point of mechanisms is to push to the product. Why would we have a step that is favored towards the reagent? The short answer is it's actually the only way the reaction works. In a mixture, we always have a smaller amount of the enolate and a larger amount of the starting aldehyde. That's going to be key to the next step of the mechanism. At this point, we've made our new strong nucleophile, the enolate, but what is it going to react with? It's a nucleophile. It could react with the acidic proton on water, but that would just send us backward in the equilibrium. That doesn't progress the reaction forward. It can't react with more sodium hydroxide. Sodium hydroxide is a nucleophile. The enolate is a nucleophile. When you put two nucleophiles together, they just kind of stare at each other. So what is the enolate even going to react with? This is why it's important that this equilibrium favors the reagent. The enolate is a nucleophile, but it's only present in a small amount. The thing that's present in a larger amount is the original aldehyde, which is an electrophile at the carbonyl. For the next step in our mechanism then, we'll take a lone pair of electrons from oxygen, drop them down to form a carbonyl. That forms too much electron density around this carbon, so we break the enolate pi bond, bounce those arrows through the alpha carbon, and use those electrons to attack the electrophilic aldehyde, kicking electrons up onto oxygen. This is classic enolate behavior. This is classic strong nucleophile behavior. This is just like a Grignard attacking an aldehyde, an alkyne anion attacking an aldehyde. And this is the defining aldol moment. This is what makes it the aldol reaction. This forms our key carbon-carbon bond in this mechanism. Now, you might be wondering why the O- didn't directly attack the carbonyl. We've seen O-'s attack lots of things before. If this part of the aldol confuses you, that's a very logical place to get stuck. It really does make a lot of sense that the O- should attack the carbonyl. How are we supposed to know that it's the carbon that does the attacking? To rationalize why it's the carbon that attacks, we go to one of my favorite ninja level pro tips in organic chemistry. The second best resonance contributor typically defines the molecule's reactivity. That's such an important pro tip. I have an entire video on just that I'll link to down below. What do I mean, the second best resonance contributor? The enolate is a series of resonance contributors, and we can rank these in order of how much they weight toward the resonance hybrid. The negative charge is by far more stable stable on the oxygen, so this is the first best resonance contributor, making this the second best resonance contributor. The first best resonance contributor weights most toward the resonance hybrid. The resonance hybrid looks most like the first best resonance contributor. But the second best resonance contributor typically defines the molecule's reactivity. And the second best resonance contributor shows the negative charge nucleophilicity on the alpha carbon. This is how we can rationalize why the alpha carbon is the one that attacked. If you'd like to brush up on all things resonance, I have a resonance playlist that I'll link to down below. The result of this aldol addition is a new carbon-carbon bond between carbon 2 and carbon 4, and an O- on carbon 4. This is the step that's very analogous to a Grignard attacking a carbonyl to make a carbon-carbon bond, or an alkyne anion attacking a carbonyl to make a carbon-carbon bond, or an enolate attacking a carbonyl to make a carbon-carbon bond. Yes, the enolate looks weird, it's got this extra double bond oxygen thing, but mechanistically, chemically, predictably, it reacts just the same as all of our other strong nucleophiles we've already seen. The one really interesting nuance to this step is, unlike other carbon-carbon bond forming steps we've seen before, this step is reversible. These electrons could collapse down from oxygen, break the 2,4 bond, and kick out the enolate as a leaving group. Carbon is almost never a leaving group. But recall what it means to be a leaving group. A leaving group separates from a molecule with a new lone pair and can be stable with that new lone pair after it leaves. Carbon with a lone pair negative charge is almost never stable. But the enolate is resonance stabilized. That makes it much more stable than we would otherwise expect, and makes it our last competent leaving group in carbonyl land. Now that we've rationalized the enolate acting as just any other strong nucleophile to form an O-, just like all the other strong nucleophile mechanisms we've already seen, we'll finish the mechanism the same way as well. We'll take the O- charge to pick up the acidic proton, file some paperwork, clean up the charges to form our final product. The beta-hydroxyaldehyde is our final product for this mechanism. If you're not familiar with the concept of proton transfer steps as paperwork, I have an entire video that I'll link to down below. It's a concept I made up to take some of the fatigue out of our long carbonyl mechanisms that often have a bunch of proton transfer steps embedded in them. The last thing to point out with our product is we have formed new stereocenters in our product. You've likely seen this before with other strong nucleophiles attacking carbonyls. The new alcohol is a stereocenter, and the carbon next to it, the alpha carbon, is also a stereocenter in this example. We have formed two new stereocenters in this product. To figure out the stereochemical consequence of a reaction, we should go backwards through the mechanism to the place where we formed that stereocenter. In this mechanism, both stereocenters were formed in our key aldol step where carbon 2 attacked carbon 4. Carbon 2 is sp2 hybridized, so when it attacks, it can attack from either the top or the bottom face without preference. The carbonyl carbon is also sp2 hybridized. When it gets attacked, it can be attacked from either the top or the bottom face, also without preference. That means we end up with a mixture of 4 possible stereoisomers. Both wedge, both dash, one wedge, one dash, the other wedge, the other dash. So that's our mechanism. The clean and simple version, deprotonate the alpha proton to make an enolate. Just like every other strong nucleophile, it'll add to the carbonyl to make an O- that we protonate to make an alcohol. Let me close by showing you 2 examples where the classic aldol really shines, and one follow-up to help you avoid the situation where the classic aldol descends into utter chaos. The first example is the example we just saw. The classic aldol is really good for self-aldols where one aldehyde couples with another molecule of itself. This is due to that quirk where the acid-base step in step 1 favors the reagent, so we have a small amount of enolate that can still react with the ever-present aldehyde to form the aldol product. We sometimes call this aldol dimerization. If you want to couple one aldehyde with itself, the self-aldol is the way to go. The one follow-up where you have to be careful is when you want to do a crossed aldol, where you couple one aldehyde with a completely different aldehyde. If you're not careful and you mix these all together under classic aldol conditions, well, we have 2 problems. The first problem is that the base can form an enolate from either of these aldehydes. We'll end up with a mixture of enolate intermediate. And the second problem is, because there's a small amount of enolate and a large amount of aldehyde, each of these enolates could react with either aldehyde without preference. And without really meaning to, you form 4 completely different products. Not only that, but with the 2 stereocenters each of these has 4 stereoisomers. You have formed 16 unique products by innocently trying to do a crossed aldol under classic conditions. This is a situation to avoid. There are ways around this. We have developed a modern aldol reaction that can do crossed aldols with ease. I have a link to that video that I'll link to down below. But there is one redemption story for the crossed aldol under classic conditions. If we start with a non-enolizable aldehyde, an aldehyde that has 0 alpha protons and cannot be deprotonated by a base, then when we mix these together, they're just going to kind of look at each other. Okay, based on what we talked about before, they'll go back and forth making hydrates and back to carbonyls, but it'll rest at the carbonyl stage. Once those have been stirring for a while, we add an enolizable aldehyde drop by drop, and the drop by drop is important. When we add in a tiny amount of an aldehyde with an alpha proton, it'll get deprotonated separated by the base to form an enolate, and there'll be a small amount of enolate and a much larger excess of the other aldehyde. That small amount of enolate will react with the much larger excess of aldehyde to form a successful crossed aldol under classic conditions. But it only works if one piece has no alpha protons and cannot be turned into an enolate, and only if we then add the second aldehyde that can be turned into an enolate. This is a very clever trick that early chemists used to form crossed aldol products when normally it would descend into chaos. This is the reaction card for the classic self-aldol reactor. Our three-phrase sentence is an aldehyde reacting with sodium hydroxide makes a beta-hydroxyaldehyde. We need to know that three-phrase sentence in all possible combinations. An aldehyde plus base makes a beta-hydroxyaldehyde. Sodium hydroxide turns an aldehyde into a beta-hydroxyaldehyde. And a beta-hydroxyaldehyde can be made when we react an aldehyde under basic conditions. Some notes for this reaction. It's best for self-aldol dimerizations or crossed aldols where one of the partners is a non-enolizable aldehyde. All of these aldol products can be dehydrated with heat. That wasn't the point of this video, but I have a separate video on aldol dehydration that I'll link to down below. And this is not suitable for a generic crossed aldol. We need the modern aldol conditions for that. Our tags for this reaction is regioselective. The base preferentially forms the enolate rather than forming the hydrate. That's really more chemoselectivity than regioselectivity, but it fits here in our regioselectivity tag. This is a non-stereoselective reaction as drawn. We get a mixture of 4 possible stereoisomers in the classic aldol. And it's redox neutral. Our aldehyde starts and ends at the 2-CZ bond oxidation level.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.